Imagine shrinking down to the size of an ant, then smaller, until you're tinier than a speck of dust. You find yourself in the vast emptiness of an atom, a universe in miniature. At the center lies the nucleus, a dense core housing protons and neutrons. Elusive electrons dance around the nucleus, inhabiting regions of space known as atomic orbitals. These orbitals are like fuzzy clouds where the likelihood of finding an electron is high. This probability distribution is called electron density. These orbitals, defined by their shapes and energy levels, hold the key to understanding atoms and molecules.
The simplest type of atomic orbital is the s orbital. Picture it as a sphere surrounding the nucleus, like a fluffy cotton ball. As we move away from the nucleus, the electron density, our chance of finding an electron, decreases. However, the s orbital maintains its spherical symmetry. The probability of finding an electron is equal in all directions from the nucleus. But here's the intriguing part. Not all s orbitals are created equal. As we move to higher energy levels further away from the nucleus, the s orbitals get larger. Imagine inflating the cotton ball. It retains its spherical shape but encompasses a greater volume. This difference in size reflects the higher energy of electrons residing in these larger s orbitals.
Unlike the spherical s orbitals, p orbitals introduce us to directionality in the quantum world. Imagine two identical balloons tied together at their ends. This dumbbell-like shape represents the basic form of a p orbital. There are three types of p orbitals, designated as px, py, and pz, each oriented along one of the three-dimensional axes, x, y, and z. Imagine these dumbbell-shaped orbitals pointing along perpendicular directions in space. Each p orbital has a region of zero electron density at the nucleus, called a node. Think of it as the pinched point where the two balloons are tied. The p orbitals, with their directional nature, play a crucial role in forming chemical bonds, as we'll see later. Their ability to overlap with orbitals of other atoms dictates the geometry of molecules and ultimately influences the properties of matter.
Section 4. Navigating the complexity of D and F orbitals. Venturing further into the quantum realm, we encounter the D and F orbitals, with shapes far more complex than their S and P counterparts. Imagine intricate balloon animals with multiple lobes and nodes twisting and turning in space. The D orbitals, 5 in number, exhibit a variety of shapes, some resembling four-leaf clovers, others like dumbbells with rings around their centers. These complex shapes arise from the intricate interplay of attractive forces from the nucleus and repulsive forces between the electrons themselves. The F orbitals, even more complex and numerous, 7 in total, are like intricate sculptures, each with its unique arrangement of lobes and nodes. Their shapes are challenging to visualize, even for seasoned chemists, and their description goes beyond the scope of our current exploration.
Section 5. Quantum numbers. The address system of electrons. To navigate atomic orbitals, we use 4 quantum numbers like an address system for electrons. These numbers provide a unique identifier for each electron within an atom. The principal quantum number, n, determines the energy level of an electron. Higher values of n correspond to higher energy levels. The angular momentum quantum number, L, defines the shape of the orbital. For a given n, L ranges from 0 to n-1. Each value of L corresponds to a specific orbital type. L equals 0 represents an s orbital, L equals 1 a p orbital, L equals 2 a d orbital, and L equals 3 an f orbital. The magnetic quantum number, ml, specifies the orientation of an orbital in space. For a given L, ml ranges from -L to +L. Finally, the spin quantum number, ms, describes the intrinsic angular momentum of an electron.
Section 6. From orbitals to atomic structure, building blocks of matter. Understanding atomic orbitals and their quantum numbers is paramount to comprehending the structure of atoms and the interactions between them. The arrangement of electrons within these orbitals, governed by the rules of quantum mechanics, dictates an atom's chemical properties, its ability to form bonds, and its behavior in chemical reactions. The periodic table, a cornerstone of chemistry, is a testament to the predictable patterns that emerge from the electronic configurations of different elements. These patterns, rooted in the principles of atomic orbitals and quantum numbers, allow us to predict the properties of elements and design new materials with tailored characteristics. From the vibrant colors of dyes to the conductivity of metals, The intricate dance of electrons within atomic orbitals underpins the diversity and complexity of the material world. Our journey into the heart of the atom, guided by the principles of quantum mechanics, reveals the elegant simplicity that underlies the vastness of the cosmos.